We're going to go ahead and continue to talk about how to take derivatives, but now we're going to talk about derivatives of trig functions. Derivative of sine is cosine. The derivative of cosine is negative sine. Now, we can go ahead and go back and do the proof of this using our definition of a derivative. F of x plus h minus f of x all over h. Your limit as x approaches 0. Now what we're doing with this one here is using the sine of two angles added together. And that's how we come up with this here. That formula goes back to your pre-calc material. Now, all we're going to do from here is we know we're going to want to try to use our basic trig limit. Our basic trig limit says, okay, we have the sine of h right here. We need to put that over h. So that's where we're going to take this middle term right here, and it comes out here together. These other two terms, this one right here, oops, I want a different color. This one right here, and this one right here, we're going to put over h, and that's what we have right here. Now this proof should be somewhat familiar to you because it should be almost the third time you've done this or something similar to it with your homework and your initial packet. Now, right here we have sine h over h, which I write down below, times this. This is your basic trig limit. You should remember that your basic trig limit is 1 times the cosine. Now here we can pull out our sine. When we pull out our sine of x, we get this times this here. What we have in the parentheses is another one of your limits that was right next to your basic trig limit. And when you look at your limit as h approaches 0 of this, it ends up going to 0. So you get the sine of x times 0, which is 0, so we don't need to really be concerned about adding that, plus the cosine. So we just get cosine of x. You're going to do very similar proofs for the derivative of your cosine and other trig functions. So go ahead and pause the video while you take a look at this derivative. Once again, for this one here, you're going to come along and you're going to take your exponent, put it in front, because we have a power here, so we'll use the power rule. Put your exponent in front, you get 2x to the first, then it's minus 2. Derivative of cosine of x is negative sine. So your negative times your negative is positive. So here is your derivative. Now, derivatives are rates of change. Sometimes derivatives can talk about population growth, production growth, water flow rates, velocity, and acceleration. When you're dealing with your position function, you should remember from what we've done before that the derivative of a position function is velocity. Now, that's what the actual velocity is. However, if you were looking for just average velocity is just change in distance over change in time. Or, since our initial function is position, be like f of b minus f of a over b minus a. Just your slope formula, slope between any 2 points. When you're looking for acceleration, what do we have to do to our velocity to get acceleration? We want to take the derivative. Now, if we have our initial function, which is position, and then we want to take, and this means your second derivative, meaning the derivative of the derivative, what's that represent? Well, if you take your derivative of position, you get velocity, then you need to take your derivative again of velocity, which is acceleration, so it represents acceleration. So, here, if this is our initial position function, And by the way, depending upon the problem you're dealing with, G may be the 9.8 if you're dealing with meters per second squared, or depending upon your units, it may be about 32 feet per second squared. Your velocity of this, remember, is just your derivative. So you got to take your derivative, put your exponent of 2 in front. 2 times that negative a half is just the negative. You'd still have g, you'd have a t to the first. Derivative of this here is v naught. This is your initial height, that's just a constant, that goes to 0. Now, when you go ahead and take a look at a projectile like this, what's your slope at the highest point? Well, your slope at the highest point would just be a horizontal line, so it would be 0. Here, your projectile is going up. So what's velocity when you're going up? Well, if your projectile is going up, the slope of your position, which is in red, is given to you right here. That's your derivative. That's got a positive slope, so you know your velocity is positive. Here, when you're coming down, your slope is going down, so your velocity is negative, which makes sense since our distance to the Earth is decreasing. Now, if we go ahead and find the acceleration, that's just your derivative of the derivative. Well, here we had our derivative, so you got to take your derivative of that again. When we take the derivative of that again, the derivative of v is your acceleration. Going to put your exponent in front, so you get a negative g, t to the 0, which is 1, plus 0, because the derivative of a constant is 0, so that's your acceleration, which is acceleration due to gravity. So, here, we want to know when the diver hits the water. Well, when the diver hits the water, that means your height is 0. Here's your height. You go ahead and plug in 0. It's just a nice normal quadratic. You could use quadratic formula, or this one here does factor quite nicely. It's easiest if you divide everything by negative 16. Do you have to? No, but it's easiest. It factors into a 2 and negative 1 for your answers. Well, we can't have a negative times, so you know in the context of the problem that it has to be 2, and the units is seconds. Part B, they're asking you to find the diver's velocity at impact. Well, your velocity, once again, is the derivative of your position. So you need to go back up to your original function, right here. Take your derivative, meaning remembering to put your exponent in front, decrease your exponent by 1, and remember the derivative of 32, which is a constant, is 0. So we now have our velocity equation, or function. We want to know what's our velocity when we have impact, which is at 2 seconds. So you plug in 2 here. 2 times negative 32 is negative 64, plus 16 gives us our negative 48. In the context of our problem, it would be feet per second. So our velocity at impact is negative 48 feet per second. And once again, our answer being negative should make sense since the distance is decreasing right before we have impact. Now, suppose you had f of x being equal to, say, an x plus 5, and I'll put a 2 here, all squared, and you wanted to go ahead and find your derivative of that. You'd first of all have to FOIL that out. Then you'd want to go ahead and take the derivative of the green.